Hello, my name is Andy Hales at the University of Mississippi, and in this video we are going to look at how to calculate a correlation between two or more variables in R. So for starters, we're going to use the tidyverse and correlation packages. We'll read in the data, and then first things first, we want to look at a scatter plot of the thing we're about to calculate the correlation between. And in this example, we're going to look at people's number of siblings, either 0, 1, 2, and so forth, and the number of Skittles that they estimate are in a regular size bag. Now, you'll notice when we create this scatter plot in ggplot, we get a little warning message telling us there's a missing value. Good to know. But also on the scatter plot, you'll notice because siblings is an integer, we might worry about overplotting where points are printed on top of each other. And a convenient technique for addressing that is called jittering. So if we replace geom point with geom jitter, it'll add a little bit of random noise to each of these data points. This is especially useful when you have Likert scale responses and it's a coarse-grained measurement. So if we jitter these, we see the same general pattern, but a little bit less overplotting here, which is good. So just kind of eyeballing this, you might discern a slight positive correlation, but we don't know if that's statistically meaningful or not. We might be interested in testing that correlation, and to do that, we would use core.test from base R. And we just give it the name of both of our columns from the same data set here, siblings and estimate, and we get this output for the correlation. We have a t statistic associated with the R value for the correlation, degrees of freedom, a p-value. But what we're often most interested in here is the value of the correlation itself. Pearson's R down here is a positive 0.19. So if there is any relationship here, it's a positive one, but not super strong. Conveniently, we also get the 95% confidence interval, and in this case, it largely overlaps with 0. We have a non-significant effect here, so there you go. That's the basic output for a single correlation. However, often we might have a set of variables, and it can be important for basic descriptive statistics or just to inform an audience. You know, we measured these 6 things, and if you're curious how correlated all of them are, here's a big correlation matrix where you show the correlations between all combinations of variables. And to do that in base R, you take your data frame and you use select from the tidyverse to just pull out the names of the particular variables you want to look at. So here we have siblings and estimate, the 2 variables from the scatter plot, and then a few other measures about their current feelings of self-esteem, belonging, etc. And then you pass that along using the pipe operator to core, and you tell it you want to use the pairwise complete observation. So for any 2 correlations, use all the available data that you can for those 2 data points. But if someone skipped one of the other data points, that shouldn't affect the correlation between just those 2. It's a sensible default. And then after that, we want to round it just to make it easier on the eyes. And when we run this, we get a correlation matrix, but it printed in an unpleasing way. So I'm going to adjust my window yet again here until it prints all together, and we get this correlation matrix. So it prints all combinations of variables, which in the case of output like this means half of these data points are redundant with the other half. So the correlation between siblings and siblings is 1. It's the same thing. But this column here on the left shows the correlation between siblings and all of the other variables. We saw earlier siblings is correlated at 0.19 with estimate, and then it's negatively and weakly correlated with those 3 measures of self-esteem, belonging, and meaning. And so you can go through and comprehensively find any correlation that you care about in this table. Cool. That's fine for descriptive statistics, but you'll notice there are no p-values or confidence intervals in this table. And if you're interested in looking at a particular test of any of these values, then from the correlation package, we can get that very helpful output using the correlation function. And here again, the window needs to be adjusted, but what it gives us is for all pairs of variables, so for any of the correlations in the matrix above that we were just looking at, we can observe the R correlation, the 95% confidence interval around it. So this 95% confidence interval looks familiar. We saw it a moment ago. The associated t-value, degrees of freedom, and p-value. You'll notice these degrees of freedom vary a little bit. That's because earlier we saw that someone apparently skipped one of the items, so we have a little bit of missing data, and that affects just the observations that are missing, which is why the degrees of freedom bounce around a little bit here. So there you go. That is how you look at correlations in R.